Welcome dear students to this first online teaching content of the electrodynamics course, remaining topics which we are going to discuss. This is the topic number electromagnetic wave propagation dash S8 section 8. This was the last topic which we were in when the break of this COVID-19 was taken. So the topic was the solution of the plane monochromatic wave equation traveling in a non-conducting medium. Dear students, before we move on, I would like to take the opportunity of this online teaching content. Now we can demonstrate the things side by side. I would like to first demonstrate just a quick review that we have been talking or discussing about how the light is emitted and how it travels. So let's take that. This is a very beautiful picture. From here you can see this is the electromagnetic energy released by some light source power. As you can see, the light is emitted in spherical three-dimensional direction, but we take a light ray. This is the light ray which is traveling. So actually there are spherical fronts all around the source, emitted and blasted into space. Now among that spherical front, we take small portion of that. This is a small portion. It is very curved near to the source, but as it moves on, the curvature of this small the area of that spherical surface gets flatter and flatter. You see here the sun ray coming from the sun at a very extremely large distances. When reaches, it almost become the huge. If you take the big spherical wavefront, then these wavefront becomes almost parallel, and we take the direction of that parallel spherical wavefront, which is now is a plane wavefront, and moving right in the perpendicular direction to the plane. Here the energy dissipation is also being demonstrated. That is, the energy or the intensity of the wave is given by the electromagnetic energy by the area of cross section. So if the total area of cross section of the sphere we take, which is 4 pi r naught square, and if r naught is the distance, r, 2r, 3r and so on, if you take the intensity decreases by the square of the multiple of the r, here 1 by 4th, 1 by 9 and so on. So this is a very beautiful demonstration which can give you the idea how the light is emitted, since we are in the Maxwell equations, which is looking for the solution of the propagation of the electromagnetic wave, or the wave equation is being sorted out by the Maxwell. Okay, now we move to another very beautiful animation. Here we have, you can see the E field which is along the vertical. This is the dynamic picture. We can see the animations. It is the linearly polarized wave, electric field and the magnetic field components. We will be considering the plane wave, which is having a plane wavefront in the coming topic. So you can see that we can control the motion of that animations, and you can see beautifully the E field is perpendicular or orthogonal to the H field. So here is the H field, which is the blue one, and the red one is the E field. So both are propagating side by side but perpendicular to each other, and the direction is also perpendicular to the E and H. Okay, now let's move on. We started with the wave equations which we lastly worked out for the space dependent coordinates only, which was the del square of E of S, the electric field, plus omega square epsilon mu E of S, which is electric field in space part only. Time dependent part is not considered. Since we are considering here the non-conducting medium, so we take that the volume charge density rho is 0, the current density is 0, and also the conductivity is 0 in the medium. Medium has the following 0 values, the values of these quantities. So let us now consider that the wave is now moving in the positive z direction with a plane wave having its the resultant amplitude. This is now the previous animation you saw, that was the linearly polarized wave traveling along the certain direction. Now we take the E naught is the amplitude, is the maximum value, and it has two components, E naught y and E naught x, and this wave is traveling along the z direction. So E naught field vector has now two components in this case. So E of S, which is space part, is moving along the z. So putting, since now it is the, we are taking the del square, will be now we along the one dimension, so we take the exact differential of the 2 ES along the z by dz square, and E naught is being now having the two components, E naught xi plus E naught yj. Okay, so this is what we have gone through. That I will go quickly through that, and I will come to the that part, but we left last time. This was the wave equation we got, and then we again put the function E of Sz that was defined as the amplitude times the space part, which is e raised to power plus minus j omega epsilon mu square root times z. This is the exponential propagation function, which we already defined the previous topics, which we have done in the Maxwell equations. So E of Z, if you replace E naught, which is equal to E naught xi plus E naught yj, and rest of the values are there. So since we have defined the E actually is a space-time dependent function, so we have E of Z and time as well. If we include the time as well as the e raised to power minus j omega t, j is obviously the complex part, which is under root minus 1. Then we put this value, and then we get the putting equation 4 in equation 5 here. So what E of zt, here is zt, we get E naught xi plus E naught yj and e raised to power plus minus j omega epsilon mu z minus j omega t. So actually we are multiplying it, so it will ultimately come when the power of the exponential will be added here, plus minus j omega t. So similarly, we have now the for the B part, the magnetic field, which is a function of RT or ZT. B of Sz is in the space part, and e to the minus j omega t. Now the Maxwell third equation given as the curl of E, which is now we consider Z as a function of Z and T, is equal to minus delta B by delta T, which is a ZT. This is equation number 7. And if we take the right hand side by taking the differential of the B of RT or B of ZT, then we get the result, which is differential delta by delta t. If we differentiate this equation by respect to time, then we get j omega B of Sz e to minus j omega t, and putting down these values back here in the equation 7, but we get the curl of E of z e raised to minus j omega t is j omega b of s z, right hand side and left hand side both side. So this was the actually E of zt. So we replace the function E, electric field function, as a E of sz into e raised to minus j omega t. So j e minus j omega t is cancelled out on the both side. So we are left with the curl of Es is equal to j omega b of s, which is the space dependent part only. Now let us express first we take the left hand side of the equation, this 9 above 9, in its component form. When we take that component form, so I j k, we determinant form, we take the matrix curl of s. So del is here delta by delta x, delta by delta y, delta by delta z, and similarly what we have for the E of sz, it is the E of sz which is equal to E naught xi plus E naught yj times. So we multiply these to the I component is multiplied with the e raised to j omega square root of the epsilon mu z. So both this is multiplied with the both, and we put the respective coefficients of the I here. E naught x is plus minus j omega square root of the epsilon mu z, and similarly E naught y e raised to minus plus minus j omega square root of epsilon mu z. While the z component in this E of sz is missing, which is 0, so we put over here the 0. So the next page, which we go to this page number 3, I will be mentioning the pages because I may extract the audio and may also add the audio for those students who can't download the videos, so that will be easy for them. So we are in page 3 sorry, of the S8, the section 8 of the electromagnetic wave propagation. So if you take the curl of E of sz, so that is self-explanatory, very simple. We have done in the class, and you know it, so I'm not going to take the time over here. So simplifying that, what we will get at the end here, the curl of I will just then go through here, that minus curl of E of sz minus I unit vector E naught y plus j. It comes with the internal cross product what we have taken. So the final result is the minus I E naught y plus j E naught x times the plus minus j omega epsilon mu square root times the e raised to minus e raised to plus minus j omega epsilon mu under root square root times z. So r we can write here this j, the k, this whole equation, which is the I minus I E naught y plus j E naught x, as a k cross of, if we take the cross product of this with the E naught x I plus E naught y j, then we get the same result, which is this one minus E naught I. So we put it E of sz, k cross E of sz. If you take the cross of E of sz, then we get k cross of E naught xi plus E naught yj is for that function. So this was the final result of the curl of E of the left hand side, the last equation. So curl of E of sz is given by, this is the the required result, because over here we have this altogether solution E of sz contains e raised to plus minus j omega epsilon mu z. This whole term is taken, this whole term is actually E of sz. So we are left with this additional part, which is here, this one that is being multiplied over here, plus minus j epsilon mu omega. So now putting the above equation of the value in equation 9. So what we get means putting the both left hand side and the right hand side. So let's take the right hand side over here, j omega b of sz plus minus j omega epsilon mu, and putting that whole equation. So omega omega is cancelled out, j is cancelled out. So b of sz now expressed in terms of the e of sz, which is equation number 10. So b of sz is given by plus minus under root epsilon mu k cross e of sz. So further, if we take that the putting the e of sz value over here, we get plus minus epsilon mu k unit vector cross k is the direction of the wave which is propagating along that z direction, plus minus omega epsilon mu under root times z minus omega t. So actually this is the j is taken common. We can put here the bracket, but anyway, if we let me mention that there will be so here we should put something like that here. Here the j is common. Okay, all right, so let's move on to see that. Okay, so that is the here I have further clarified that one, so that let me just take that out. That graphic part should be clear. I think let me clear that out. Just wanted to explain that. Okay, so let me draw back. Okay, so that is the b of z. Now b field is now solution has been found, that how the b field propagates, that is the as the epsilon mu under root k cross e raised to power j omega plus minus j omega epsilon mu z minus omega t. So we got the both solutions for the E and B solution of the wave equation. Now the equation 6 and 11 are the solutions. So we mentioned that the equation 6 last, which was about E, and equation 11 which is about the Z, B. So this is the solution we have found, E, Z and B, Z fields. In both equations 6 and 11, wave is propagating along the positive Z direction. So let us assume that the wave, this was the specific dimension we were talking about, but the wave actually travels in all directions in a spherical dimension. So what we have now, let's now take that the wave is moving in an arbitrary direction u, some u with a unit vector, where u plays, the unit vector plays the same role as the k plays. So the z is now replaced by u, any arbitrary coordinate, which is u is some vector and u is, it will be magnitude, and u unit vector as direction. So we replace now the z is equal to r cos theta here. Now r is some position vector, u is the direction, so the projection of r on the z axis is r cos theta, which has also the same direction of the u. So we take the u unit vector dot r unit vector, which is the, we take the projection of that is equal to r cos theta. Now the field vectors are expressed as, now E field is E naught eastward, the whole this function u unit vector dot r minus t, and similarly B field function as a plus minus epsilon mu u unit vector cross E naught as a, and the whole function as we write previously. Now let us say that the k, this is the term k vector is equal to plus minus omega epsilon mu square root with a u unit vector. This whole term, the quantity we take here, the here this one omega times epsilon mu under root as a k, some vector, then the E field vector will having position vector r, E naught will be equal to E naught is for j times k dot r minus omega t. So similarly B will be equal to k, this is total vector k, because here we replace the B. So if you multiply and divide by omega, you get the omega times epsilon mu, which is k and the magnitude, but the unit vector u is also the direction along which that vector is propagating. So it will be now the k vector divided by omega times the same function. Now where k is now called a wave vector or a wave number. If the wave is moving with the constant phase, so let's say k dot r minus omega t is equal to some constant quantity. Now let us differentiate this equation 16 with respect to time, and what we get, d by dt of this whole constant phase will be, r is now the time dependent, while and t, these two factors, while the derivative of the constant here will be equal to 0. So k will also be constant for that time independent quantity we consider, because k was equal to omega times epsilon mu under root. Here we have the k times dr by dt minus omega. Dr by dt is now the speed, or the speed of the wave, given by omega by k. Since k is equal to omega times epsilon mu under the square root, then we have under the root, then we have the speed of the wave is given 1 over epsilon mu square root, which gives the speed of the wave, and this is called the phase velocity in a medium. So far, if you take the vacuum, epsilon and mu are replaced by epsilon naught and mu naught, it becomes the speed of light, which is c. So that for the vacuum, which is 3 into 10 to the power 8 meter per second. Okay, so with this we reach to the end of this topic, and we will continue inshallah in the next topic. Thank you.